No, I think so though. The one where it was like what muscle you with your right eye going left, I definitely thought of the wrong place. And so I felt bad. I was like, what's gonna happen? I got that wrong. I can't remember. I don't know. That's the last one. I think that was okay. And I got one. The little crystals in the vestibule. So then like as we move around the crystals, so the head is able to be aware of like your sense and thoughts. But are those special sensors? Well, because then it like rubs against the hair cells or the populares. Oh, sorry.
All right, guys, it is about that time. Let's go ahead and get started. All right. So last time we, I think, had left off talking about the Wittig reaction, right? And so we said the Wittig reaction was a way that we can make alkenes, aldehydes, ketones, mix them with the appropriate Wittig reaction. One thing that's kind of cool is you can basically sort of program your Wittig reagent to put not only the type of R group that you want, but it'll also allow you to really distinctly figure out exactly where you want to put the double bond. All right. Just to refresh you a little bit, let's go ahead and do a practice one. Do an aldehyde this time. All right, Wittig reaction. Let's see, Wittig reagent, excuse me. Oh, let's do something creative. A little different than just an extra methyl group or something. Okay, so this is the reaction we want to proceed, right? Our Wittig reaction, our Wittig reagents on the top of the arrow. Remember, you can't just order Wittig reagent from a supply place. You got to make it. So let's go ahead and make the Wittig reagent first, and then we'll go through the mechanism of this example. All right, so what do we need to make a Wittig reagent? Y'all remind me. There's two basic things. You need triphenylphosphine, right? Which is that guy. What was that? Did y'all hear something?
You recording?
I'm recording, yeah. Sounded like one of those, you ever watch one of those ghost shows where they use the ghost like little radio thing? That's what it sounds like. Anywho, we're actually not going to use an organolithium just yet. There's something else that we use before we get to that. Going to use an alkyl halide. And again, which alkyl halide do you use? Well, you use the one that corresponds to whatever R group that you want. So in this case, we would use, a cyclopropyl bromide or cyclopropyl chloride, right? Phosphorus nucleophilically displaces the bromine. Since phosphorus is donating electron density, it goes from neutral to positive. Now, the last thing we said was, though, we wanted to make this carbon right here negative. And to do that, we have to have a base that'll pluck that H away. Now, what exactly is the base that we need? What's that? I heard somebody say something. I know it wasn't the ghost box this time. There's a very specific base that we needed here. Matt, you alluded to it earlier, I think. We need an organolithium, specifically which organolithium? Methyllithium, ethyllithium, propyllithium, pentalithium. One I've omitted, perhaps. Ah, you see what I did there, didn't you? Yeah. Butyllithium, there you go. Yeah, butyllithium is the one of choice. It's one of the few organolithiums that you can actually order. So this guy will act as a base. Grab that proton. Bada boom, bada bing. You have your Wittig reagent. There you go. So that's how we made the Wittig reagent. Now we can actually use it. All right. So let's walk through the mechanism of the Wittig reaction. All right. Again, you guys tell me. You're experts by this at this point now. How does the Wittig reagent interact with your aldehyde? Mm-hmm. So yep, exactly. Cause the phosphorus attracted to the partially negative O. And what was the rest of it?
The negative charge will attack the partial positive as on the carbon attached to the.
Absolutely. Yes, very good. Negative carbon can attack your strongly partial positive carbon. Right? So we said we got a funny little intermediate structure. And this is, I think, the hardest part of doing these is trying to draw them. So you have to think, even I have to think through them carefully here. So we have the O. It's bonded to the phosphorus now, which still has the pH 3. Which I can't draw. Attached to it. This bonded to your cyclopropyl group, which is also bonded there. Okay. That's the hard part. Once you get past this, it's great. All right. This is not very stable. So this is going to break apart pretty easily. That O carbon bond is going to break, move up there. This phosphorus carbon bond is going to break right there. Kind of an ugly triangle I just drew, but it works. You get that, and this is a byproduct. Okay. Y'all see how we did that? Are there any questions for how we went through and got that particular product? All right. One thing that's kind of cool again about using a bidding reagent is that you always know where your double bond's going to be. And that can give it certain advantages. All right. We're actually going to do a comparison now, a couple of different processes. All right. Let's take this. All right, we're going to take a look at cyclohexanone. And let's say we want to do a synthesis here. Let's say we want to make this using cyclohexanol. Instead of having a double bond O, we're going to have one extra carbon up here. Now, as it so often turns out to be the case in syntheses, there's more than one way to do this. There's more than one way to get there, right? So we're going to compare a couple of different pathways here. All right, the first one is going to be going through an organometallic. All right, y'all remember last chapter we said one of the really good ways to get extra carbons onto another fragment is through organometallics. And you see, this structure has one extra carbon up here. All right, so that's one way to do this. All right, think back in the previous chapter here. How could you react this with an organometallic in order to get another carbon on? What could this react with? You have a ketone. Remember, we had like 3 different organometallics, right? We had organolithiums, we had Grignards, we had organocuprates. You could do a Grignard. Yeah, a ketone could react with a Grignard or an organolithium. All right. How many carbons are we wanting to add? Just one. So it stands to reason, if you're using a Grignard reagent, you would use that one. All right. So you remember the formula. We do this first, and then we follow it up with proton source. That's CH3 minus, attacks this carbon, drives a pair of electrons up, protonated by water. So we get that. That ring a bell? Hopefully it does. All right, now it's not our final product though. We still haven't gotten to our product. How do you get from here to here? Organic 1 stuff. H2SO4, very good. Yeah. H2SO4. That's going to dehydrate. So you're going to lose this OH, and you're also going to lose a beta hydrogen, right? And there is a beta hydrogen over there, so you absolutely do make that product. However, there's a little caveat here. What's the caveat? You do make this, but it's not going to be resonance. Let me remind you of the mechanism. I'll just draw the mechanism for this out here. Remember that OH gets protonated. Make water, water leaves. Then our HSO4 minus grabs a beta hydrogen. And these electrons swoop down. And that's how you make that. All right. Just a little reminder of the mechanism that we use for that last step. All right, now, what's the one little kind of annoying factor that we have to include here? Yeah, exactly. This is not the only type of beta hydrogen you have, is there? Right, we have them here and here as well, right? So that's not the only product you get. You also get this. And in fact, out of these two, which one's the major product? The one on the right, yeah. So that gives you your target. But number one, it's a mixture. And number two, it's not even the major part of the mixture. So how efficient is this in this particular case? Not very, right? Cool. Well, not cool. All right, but cool that we understand. All right, so let's see if there's a better way of doing this. Spoiler, there is. In fact, you can do this and get 100% this product. You can get that pure, no mixtures. How can you do that? You can do a Wittig reaction. Yeah, absolutely. If you did a Wittig reaction, using this Wittig reagent right over here, that ensures that you will get this product and this product only. Because in the course of the mechanism, this negative carbon always attacks there, and this positive phosphorus always attacks there. You're not going to get any interaction here or here, right? So that's one major advantage a Wittig reaction has over using organometallics when it comes to making alkenes. You have much more control over exactly where the double bond goes, and therefore you get better yields, which means more efficiency, more money saved, and most importantly, less work for you, the chemist. Does that make sense? Are there any questions about that one? All right. All right, let's keep on rolling here. More reactions with aldehydes and ketones. We can also react aldehydes and ketones with amines. All right, remember amines have carbon-nitrogen single bonds. All right, there's a couple of different ones that you can do. The first one is reaction of primary amines. All right, so let's just say we had, I don't know, we'll just use acetone. That's a good one. When we react it with amines, we set it up like this. You have the amine. We'll just use that one. We use ethylamine. And you have to have it in a mildly acidic environment. Plus, you don't want it too acidic because, well, you'll see later on why that's the case. But mildly acidic, a little bit, you know, probably pH of 5 or so. Right? Okay. Let's see how this proceeds. All right. Look at your amine. It's going to do something. What do you think your amine can do here? hint. It's very much in line with previous things that we've seen. Same song and dance we've seen before, yeah. The nitrogen and its electrons can attack your carbonyl carbon. And it's going to cause these electrons to move up. All right, it gives us a negative O and a positive N, two charges. We need to satisfy both of those charges. Oh, wouldn't it be nice if we could satisfy them both in one step? Laid out the breadcrumbs for you, you know, the leading context clues with the tone of voice doing teachery stuff. You can actually satisfy both of these charges in one fell swoop. What do you think you would do? Well, what would oxygen like? How could oxygen satisfy a negative charge? What have we been doing to it? What's that? Protonating it. So oxygen wants a proton. What about your nitrogen? It's got a positive charge. What would it like to do? Get rid of a proton. So, hey, guess what? It works out. You get a proton transfer internally. And it makes them both happy. And if you didn't have this in acidic medium, it would actually stop here. This is actually a fairly stable type of molecule called a carbanolamine. But honestly, for practical purposes, we don't really have much use for it. So we're going to keep on going with our acidic environment. All right, we have hydronium. Acids like to give up protons, right? So your H3O is going to donate a proton to your OH. I'm going to be rapidly running out of room here. Make water. What does water like to do? It likes to leave, yeah, and it does so. At the same time, this happens, the water leaves, it's going to take its electrons with it. This pair of electrons that we haven't been drawing, but it's still there, on nitrogen, they can swoop down and form a double bond with that carbon. All right, I'm running out of board space, so I'm going to loop back down this way. Okay, so water left, pair of electrons from nitrogen made a double bond. It leaves us a positive H. So the last thing we need to do is satisfy that charge. Water can come in. Water was left over from this deprotonation. It can come in, grab that H. And that gives you your final product, which is that guy. Nitrogen carbon double bond. That is called an imine. I-M-I-N-E. Also, sometimes is known as a Schiff's base. Fairly old terminology, but you still see it a bit. Okay. So anytime you see the carbon-nitrogen double bond linkage, that's called an imine linkage. And you make it this way. Primary amine, aldehyde or ketone in a mildly acidic environment. Okay. Any questions so far? All right, I'll show you something pretty interesting here. All right, let me project. For all you Zoomers out there, you can see this. I'm going to highlight in your book. You can see this in your book. It's in a little section in chapter 21 talking about the chemistry of vision. So I'm not going to spend a whole lot of time on this. So I'm not going to try to bother to loop things around to get everybody connected at the same time. But take a look at that section and you'll see what I'm talking about. Enlarge this. Oh. Arching it took back to the beginning. Bogus. Careful how much I come on. Okay. That's good enough. All right, so a little bit of biochemistry. One location of this action. So, retina, specifically rod cells, rods and cones, right? The rods, you have a molecule now. From the name now, what functional group do you think you're in it? Retinol. Retinol. Say it. What's that? Retinol. Aldehyde group. I need to go now. So there's a that has an aldehyde group, and basically what happens is the retinol will react with a protein called, right? And this thing shows happening here. The little area, the protein, actually, this little, so the opposite, and it's showing to 11.7 now. All right. Know anything about proteins? Proteins have free amine groups. They have NH2s hang off of their proteins. Basically, one of the NH2 can react with the aldehyde retinol and produces a molecule called rhodopsin. And this is rhodopsin right over here. And over here, this is going to be your amine linkage that was made to be an aldehyde here. It used to be a free 2 group, has the protein. Now they're. And rhodopsin is one of the important compounds in the chemical vision. Because what happens, there's this arrangement of double bond right here. Light, rhodopsin in your cells, basically get something called isomerization. And that's around this changes from a cis to a trans. All right, what's the big deal? Well, it would actually get energy form of a nerve impulse. And this nerve impulse travels the optic nerve, and that will allow you to stir an image. Okay. Without the use of rhodopsin, this could work, and we have rhodopsin because we get amine link. So it's a pretty little real application there where you amine link action. All right. All right. So that's what happens when you have a primary amine that reacts with an aldehyde or ketone. You can also have reaction with secondary amines. And it's a very similar process with one little sort of twist at the end. Let's say we had, we'll use an aldehyde this time. Let's say we had that. And let's see, we'll use that. We'll use diethylamine, that's a secondary amine. And just like last time, we use mild acid. Okay. Most of this is going to look really familiar to the last one. All right, so based on that, tell me what to do. What's going to happen first? Carbon gets attacked by the nitrogen. Electrons move up. Okay, we get that. Then what happens? Get an internal proton transfer. Satisfy both charges, yeah. That makes carbonylamine. Okay. Now what? Yeah. You're starting to see a pattern here, hopefully. Pretty much, this is the same exact mechanism for most of the way as our last reaction. All right, so you're going to protonate the OH. You make water. Water does what water likes to do, and it leaves. And what else happens? Electron pair from nitrogen swoops down to make a double bond. Okay. We have positive charge. And then the last thing we have to do is satisfy that positive charge. Now is here is where you might see a little bit, run into a little bit of a conundrum. What did we do last time to satisfy the negative charge, or the positive charge on nitrogen? Leftover H2O comes in, and guess what? It still does. However, what did it do last time? How did it help us out in the imine reaction? Took a hydrogen from the nitrogen, right, to help satisfy this positive charge. Well, that's all fine and dandy for imines, but not so good here. Why? Why can't we take an H from this nitrogen? They don't have one. Yeah, that's a conundrum, right? So we can't do that. However, what happens is it will do something else. instead of taking an H here, what it will do is it will specifically take an H from the carbon directly adjacent to this double bond. And that sets off a little bit of a domino series of events. This pair of electrons will swoop into a double bond here. And this pair of electrons will go back to nitrogen. And it makes that. That is your final product. This is called an enamine. And, you know, I guess that kind of makes sense, right? It's part alkene and part amine, so enamine. So this basically follows the imine formation right up until the last step. You can't take an H from your nitrogen. You got to take it from somewhere else. That H always ends up coming from a carbon that's directly adjacent to the carbon that used to be in your carbonyl group. So this one right over here is the one that ends up losing the hydrogen in the end. Okay, does that make sense? Again, predicting the products of imine and enamine reactions is actually pretty easy once you get some practice. And you can do it without even going through the mechanism, although I still want you to learn it. Okay. So you could take something like this, right? You see an aldehyde, you see a primary amine, that should tell you immediately what type of product are you supposed to have. Look back in your notes if you need to. Aldehyde plus primary amine gives you what? The one with an I. Imine. I'll take what I can get. All right, so this tells you get an imine. It's actually really simple. All you have to remember is that basically in the product, when you form an imine, the nitrogen and R group take the place of your O. So you still have a double bond, right? But instead of having an oxygen, you have the nitrogen and the R group attached. You do enough of these, you'll eventually be able to just look at it and predict it like that. Same thing with an enamine, although it's a little bit tougher. Right? Aldehyde and secondary amine. You know you should end up with an enamine group. All right? Just like last time, the nitrogen is going to take place of the oxygen, but it's not going to be a double bond. Where's the double bond going to be located? If you had to tell me to draw an extra line for a double bond, where would I put it? First come this one? Okay. This one
down.
Here?
No.
Here?
Yeah, I think.
Yes, you are correct. Yeah. Take these on your own time. Go through the mechanism of them. I think you'll find they end up giving you what you would think they would. All right. Any questions so far about enamines or imines? Funny thing about these guys, you can hydrolyze them. What is hydrolysis? Well, we said the other day, hydrolysis is when you use water in some way to help break up a molecule, right? You can actually take an imine, for example, and what you do is you add acid, but in this case, you want it to be strongly acidic, not mildly. This is why you don't use strong acid in the formation of amines, right? Because this will actually break them up. And you know what's nice? You care to guess what it breaks it up into? Any guesses? What's that? Yeah, that's one of them. And amine, yeah. This will actually break, this will basically reverse the reaction. If you put an imine in here and hydrolyze it with acid, it'll break it up into its original ketone and amine. So if you use strong acid in the other reaction, you just never get anywhere. That's why it has to be mild. Pretty cool. That's the product of one of the previous reactions we did. That's an enamine. Strong H3O. Again, it'll turn it back into its original aldehyde or ketone and secondary amine. So yeah, you can reverse it. Just takes a little bit of extra oomph with the acid. So it kind of makes you wonder, if you put a strong enough acid in your eye, would it destroy the rhodopsin? I don't know. It would probably destroy a lot of other tissues, so I really don't want to try that. Kind of an interesting little philosophical question. Do not put acid in your eye. All right, any questions? All right. All right. Do I want to do hydrates? They're kind of useless. I'll use the last few minutes in here to go ahead and skip forward to something called acetals. All right, this is a fairly important group of compounds. And this is also something where I hate to use the phrase, but back in my day, it was taught a little bit different than a lot of the books do this time, and it kind of bothers me. So I'm going to show you both notations. All right, so an acetal is defined in your book as being a carbon that's got two OR groups on it. And then two R groups. And it is possible that those R groups could be hydrogens as well. That's how your book defines it. And they use this term acetal as a blanket term for all this, right? When I was doing this, when I was learning it, it was a little bit more defined. These weren't H's, these were both R groups. And we had a second, excuse me, I misspoke. For acetal, they would both be H's, right? Or excuse me, sorry, one of them would be H. Sorry. Then we had something called a ketal. And that's the one that would have two R groups. Because basically, to make this, you start off with an aldehyde, right? To make this one, you start off with a ketone. You get it, ketone, ketal, right? But now a lot of textbooks have sort of lumped these all together under the term acetal. So that's what your book's going to do. That's probably how I'll teach it. But I've just felt like, compelled ethically, morally, obsessive compulsively to, let you know about that as well. Okay, so there's also another term called hemiacetal. What does the prefix hemi mean? For all you linguistics experts out there. Like a hemisphere, what's that? Half, right, half. And this basically means half of an acetal. So we can have our two R groups, or H. We have one OR, and then we have one OH. Yeah, exactly. All right. Basically, on the road to get to an acetal, you basically pass through a hemiacetal. So it's kind of a nice, useful little milestone to sort of look for, like if you're doing the mechanism of an acetal formation. If halfway through you see a hemiacetal, that's a really good sign. That means you're halfway there. Okay? All right, well, let's see how we actually make it. All right, so to do this, we start off with an aldehyde or ketone. We'll just use acetone here. And what you need is, first of all, an alcohol of some sort. Which alcohol? Depends on what you want to make with it. Let's just use ethanol in this case. And one thing that's very important is if you want to get a full acetal, you got to have two equivalents of it. And then you have a strong acid, usually either H2SO4 or paratoluene sulfonic acid. Okay? Just for fun in this case, I'm going to use sulfuric. All right, now this one has a bit of a longer mechanism. It's divided up really, I can divide it up into two phases, all right? Both phases begin and end with action of the sulfuric acid. At the end of phase one, you have a hemiacetal. At the end of phase two, you have your full acetal. All right. Let's see how far we can get with this one before we run out of time. Like I said, each phase begins with the action of sulfuric acid. So sulfuric acid is going to do something here. What do you think it's going to do? Well, what do acids like to do in general? Don't let me ask the question. I'm going to ask it. What is a Bronsted acid? If there's nothing else we're going to accomplish by the end of the year, you guys are going to know what Bronsted acids and bases are. What do Bronsted acids like to do? They like to donate protons. Yeah, and that's what sulfuric acid wants to do. It wants to give a proton away. What do you think can accept that proton in the ketone? Yeah, you're right. That makes you uncomfortable. Yeah. And that's important because what that does is that makes this carbon more reactive, right? Another thing to note about this is actually an equilibrium reaction, so I'm going to draw equilibrium. Right? So it gives you a protonated oxygen. That's going to increase the pull here, and it's going to amplify the partial positive here. So what happens to that carbon? We're going to finish phase one, even if we go a minute later. So what can attack this carbon? From up there. You guys know this. Partial positive carbon. What can be attacked or what can be attracted to it? Alcohol. What part of the alcohol? Which is where? Yeah, partial negative on oxygen, right? So your alcohol attacks that carbon, drives a pair of electrons up. We get that. And then we can satisfy the positive charge. HSO4 minus can come back in, grab that proton, and that's the end of phase one. So phase one begins with action of the acid catalyst, and it ends with the reformation of the catalyst. Plus, this guy, which if you look closely, you'll notice is a hemiacetal, or in this case, a hemiketal, if you would like to use that terminology. Okay. All right, we're out of time, so we'll pick up the rest of this on Monday. Are there any questions before we leave today? All right. In that case, have a good weekend. Thank you, Matt. You helped propel class along today. I appreciate that.
We have a genetic step after this, everyone.
Oh, a genetics.